Hi, my name's Max, and the paper I'll be presenting is called Assortment Optimization under Variance of the Nested Logic Model. In class, we considered the multinomial logic model for consumer choice. Presented with an assortment of products, consumers apply a weighted random utility function to choose their favorite, and each product has an underlying attraction value that influences its likelihood of being chosen. We solved the optimal assortment problem, or which subset of products should be displayed in order to maximize revenue, by showing that the optimal assortment consists of some of the products that have the highest revenue. And our in-class model assumed that products were all sort of in a common category, but this gave rise to what we called the blue bus, red box bus paradox. So an indifferent consumer might be unreasonably swayed by the introduction of a very similar product. One way to solve this problem is by grouping the products into nests, like car and bus. The consumer first chooses a nest and then chooses a product from within each nest, and if we pick the probabilities right, we can recover the intuitive probabilities in this example. Davis and his colleagues consider this more general model in their paper, and I will call the problem that arises the Nested Optimal Assortment Problem, or NOAP. In their model, we have M product categories, or nests, which are indexed by I, and within each nest there are N products indexed by J, and we're going to assume that they are ordered by revenue. Each product has an associated preference weight. There's a preference weight associated with no purchase option as well. And we must decide the assortment of products to show in each nest. So according to the model, the consumer first chooses a nest, I, and then the customer will choose a product within that nest with a probability that's given by this expression that we know from lecture. But the way that the customer chooses their nest is given by yet another logic model, and in this case, the attractiveness of each nest depends on the products that are displayed in it. V0 is the preference rate of choosing no nest at all, and gamma is the overall nest dissimilarity parameter. So a larger gamma will indicate that the products in the nest are highly varied, magnifying the nest's preferability. Given this information, we're ready to formulate the NOAP. We start by writing down the expected revenue from offering a given assortment, and then we take the inner product over all of those assortments and the likelihood of each nest being chosen. Then what we'll try to do is manipulate these assortments in order to generate the optimal highest expected revenue. The key result of this paper is that the tractability of this problem depends on two sets of parameters. First, when the non-purchase options within each nest have zero attractiveness, then customers are always going to purchase something once they've selected a nest. And if we remove this assumption, it complicates the problem. Second, when the dissimilarity parameters are on 0, 1, we assume that all of the products in a nest strictly compete with each other. So if we introduce a new product, it's going to make the other products marginally less likely to be picked. Letting gamma exceed 1 allows for synergistic effects such as loss leaders, and this will complicate the problem. Hence, the authors divide this problem into 4 cases, and only one of these cases is fully solved. That's case 1 here, where they're able to show that the optimal policy has a certain structure. But if we use solutions of this form in case 2, while they aren't optimal, the authors show that there's a certain performance guarantee attached to those solutions. In case 3, we again have an NP-hard problem, but there's a certain knapsack problem that encodes the solution to it, and you can use an existing approximation scheme to find a suboptimal solution with a performance guarantee of 2. And in case 4, as expected, it is NP-hard, but we can use case 1 solutions to find a suboptimal solution with a performance guarantee, and the authors also provide a generalized approximation scheme that allows you to control the accuracy-tractability trade-off. For the remainder of this presentation, I want to introduce some of the mathematical ideas used in cases 1 and 2. So if we linearize the objective function that I gave a few slides ago and manipulate the max function, we are able to express the NOAP using this linear program. The problem is that this linear program has too many constraints. Each SI, that's a subset of n, has exponential cardinality, and that makes this problem intractable. Instead, we're going to restrict our attention to a subset of possible assortments so that we have fewer constraints here and we can solve this problem in a reasonable amount of time. In case 1, the authors show that the optimal assortment is always a nested by revenue assortment, meaning that the optimal assortment in each nest consists of some number of the highest revenue products from that nest. This greatly reduces the size of the solution space. In lecture, we actually proved an analogous result for the simple case where we only have one nest with a neutral nest dissimilarity parameter. But in the general case, the proof approach is a little different. The authors show that given an arbitrary assortment where at least one of the sub-assortments is not nested by revenue, then we can remove the lowest revenue product from that assortment and we will get an assortment that has a strictly larger expected revenue. The sketch of this proof is that we write down the revenue associated with the original assortment, and then when we remove one product from one of those sub-assortments, it's going to decrease the value of both the numerator and the denominator of this expression. And further algebraic manipulation allows the authors to show that the denominator decreases faster. In other words, the entire expression is going to end up having greater expected revenue. In case 2, we allow gamma to exceed 1, and this means that the optimal assortment is not necessarily nested by revenue. The example they give here has just one nest, and if you look at just the nested by revenue assortments, then the optimal assortment is to offer just product 1 here, which has very high revenue associated with it. However, the globally optimal solution is actually to offer product 1 and product 3 together, because including this low revenue product 3 increases the probability that customers will choose nest 1 over the no nest option, which has positive probability here. So to guarantee optimality, we have to examine all of the possible assortments in each nest. This means that the problem is NP hard. However, Davis and his colleagues are able to show that the expected revenue ratio between the globally optimal assortment in case 2 and the best nested by revenue assortment, which we saw in case 1, is never larger than this quantity alpha. Here, rho is an upper bound on the ratio between the product revenues, and kappa is an upper bound on the ratio between the attraction values within each nest. And we can see that this inoptimality ratio will approach 1 when the revenues of the products within each nest are similar. The way that this bound is derived is by considering the original NOAP linear program. Given the globally optimal solution to this problem, xy, it's not too hard to show that there are other feasible solutions of the form cx, cy. And the authors show the solution to the problem when we restrict our attention to just nested by revenue assortments instead of all assortments has precisely this form, where C equals alpha from the previous slide. So because this is a minimization problem, alpha x will become an upper bound on the optimal solution to the unrestricted LP. I found this to be a very interesting paper. It certainly rewards a patient reading, and I wish that I could have presented all of the mathematical arguments in detail. The notation is terse. It requires a lot of kind of paging back and forth, but it's precise. The Logit model has a lot of intuitive appeal, but for it to be realistic, I would be interested in how parameter estimation and data collection could be done. Another natural extension of this paper would be to have 3 or an arbitrary number of nested layers. So the innermost layer could be products, next product categories, next store locations. Of course, this would severely increase the size of the solution space, but I think it would be theoretically interesting. And along similar lines, this model does not consider buyer profiles at all. We saw in lecture that even in the single nest case, maximizing expected revenue over diverse buyer profiles greatly complicates the problem. However, I wonder if you could reuse some of the performance guarantees that are given in this paper to derive heuristic solutions to the case of multinomial nested logic with buyer profiles as well. Thank you.